Hello, everyone. If you were expecting Professor Darden, sorry to disappoint, but he's had some family issues, so he's, I believe, on his way home now. And we've decided it would be better to have a little bit of a late start on answering questions than a late start on starting the entire review. So let's get started on the final exam review lecture. So this Friday, 4 days from today. So Ann Arbor times are 9 a.m. and 4 p.m. If you're in a different time zone, it's up to you to translate. Like the midterm, it ends 2 hours and 20 minutes later. And we've always had 2-hour exams. And during COVID, we've added 20 minutes for downloading, submitting, etc., asking questions on Piazza. And so if you have an accommodation, if you have SSD, then you'll get an extra hour for time and a half, or an extra 2 hours for double time. We're not doubling the 20 minutes. The same exam will exist for all time slots, so there's no need to choose a slot ahead of time. It's just like the midterm. Just be online and on time, start the one that's open at that time, and obviously don't start more than one of them. And then, as we did for the midterm, it's open book and notes. Well, we don't have books, but open notes, basically everything that we gave you in terms of stuff on Canvas. Just because we told you a website exists doesn't mean you can use it. But everything that's on Canvas, conceivably everything that's on YouTube, although I wouldn't want to go watching videos during the final, also, that is why it's useful to have a cheat sheet. And during a normal semester, we would have a 8.5 by 11 one-sided for the midterm and two-sided for the final. It's still a great idea to make one of those now. Even though you have the ability to look at PDFs, it doesn't mean you can find things quickly. So things that you think you might want, put on your note sheet, have them ready ahead of time. So the engineering honor code still applies. You can, if you want to, use an IDE for the written problems. The thing is, though, you don't want to spend all your time trying to get it to compile, because you get points based on what you do right. And if you have a ton of syntax errors, we might take off a point or two. But that's a lot better than having one problem done and compiling and the other problem not even started. I'd much rather have you have two problems that have all the right concepts and a little bit of syntax issues, but are basically right. You're generally going to get more points for two problems that are almost right than one problem that compiles and one that doesn't exist. So have a pencil and paper handy. Like one suggestion is make a list ahead of time, 1 through 24. Check them off when they're done. Put a question mark or something next to them if you have to come back to them later on and double check your answers. And just go through the exam and just check them off on the paper. And that'll save you a little bit of time scrolling and searching, etc. The exam is just like the midterm in format. We've got 24 multiple choice questions, 2.5 points each, 4 to 5 answers per question. There is one answer per question. There's no deduction for being wrong. So make sure you answer all of them. If you can narrow it down to, 2 choices that I don't know which one of these 2 it is, but I know it's one of these 2, then guess. You've got a 50-50 shot at that point. You don't lose points for a wrong guess, but you will get them if you guess right. Now, the exam itself, the questions are all in the Canvas quiz, so make sure that you don't submit until you're done, because you would lose the ability to read the written questions. Like the midterm, the written question starter files will be on the autograder. Like the midterm, please don't everybody try to start at 9 a.m. downloading, because the autograder can't handle that many people at once all logging in and viewing their homepage. And so, and it doesn't help you to have a starter file before you've even read the question anyway. So if you wait to download until you've read the question, since everybody reads at slightly different speeds, then we won't have everybody colliding on the server. And the real problem is our database. There's one database for both servers, and it has to answer a lot of queries to display your home page with the timing columns for all the projects. The one thing that we know happens is there's always people with display issues where because Canvas only allows us to have one setting for the time allowed, everybody is allowed basically 4 hours and 20 minutes, but everybody has a fixed start and end time that can be different. So Canvas only allows one time limit for everybody, but different people based on SSDs will have different start and end times. So it may tell you when you start, it may tell you that you started late because it's like, well, you only got 2 hours and 20 minutes and everybody gets 4 hours and 20, so you must have started late. That's just a display issue. It's just saying that because you're not getting 260 minutes, you're getting 140 minutes. So it's just a display issue there. Make sure that in fact, before you even start, make sure that the start and end times are displayed correctly if you have SSD. Once you start, make sure that it shows a countdown timer in the upper right. Make sure the countdown timer is right. If you have an SSD and somehow we missed you, if you tell us at any point up to 5 minutes before the exam ends, we can go in and add the hour that we forgot to give you. But if you wait until it's over, Canvas will not let you restart. Basically, once it's over, it's over. We could give you a new attempt with new multiple choice, and that's terrible. So if you have an SSD, it really is, I mean, it's our responsibility to get it right, but it's your responsibility also to check up on us and make sure that we didn't miss you. When you do the coding questions, if you decide that you need a helper function, like let's say you decide to do a DP problem with top down and you need the function we gave you and you need a helper function, well, then write it above the given function. Then when in the main function, when you say call the question 20 whatever helper, then it already knows what that function is. And if you need a structure, you are allowed to declare a struct inside a function or above a function. So if you decide that you need a struct to solve a given problem, then create that structure or structures above the function or inside of it. If you had two functions, like a function and a helper, then put the structure above both of them. The reason that we say this is that there are some coding problems in some semesters that can only be solved if you use a struct or potentially use a pair. And we've had people in the past when we were like, oh, this problem just requires a struct, they'll do it. And we had people tell us, I didn't know we're allowed to create a struct. Well, if you need it, create it. So now we tell people, if you need a structure, go ahead and create it. So there's a few slides here about lines. These are basically a repeat of the same slides from the midterm about what counts as a line and what doesn't. And so we've already gone through all of these for the midterm. So the curly braces never count as a line. Anything that we give you doesn't count as a line. How many lines of code is that? That's 4 lines of code as written. Now, if you could write it as a ternary operator, then go for it. Generally, our problems are not conducive to a ternary operator. But if they were, we write the line limit without it. We don't count on you using it. So we write a solution, we write a good solution, we write what we think is the most straightforward, no tricks way to do it. I still meet the time and memory constraints, but I don't pull out any tricks. And then we add a fraction of those lines to the total. So, like if ours took, let's say, 15 lines, we might say you're allowed 20 or 22 or 25, somewhere around there. So we always give you a buffer for, doing things even in a way that we didn't think of. But before we had line count limits, we'd get, problems that we solved in 10 lines of code, and we'd have people with 40-line solutions, and they're just ungradable. If you're that long, you're on the wrong track. So also, if you need a struct and you need to add something of that struct to a container, you don't have to use multiple lines to say, I create a variable of type word count, I set my wc.word equal to abc, wc.count equals 1, and then push back wc. That takes 4 lines of code. Declare the structure, equals, equals, and push back. Well, here we show how to do it with 1 line of code. So the line count equals 5 is saying, well, hey, you used up 3 lines to create that and 2 lines here. But if you had done it with declare a structure, set the word, and set the count, that would have taken 3 extra lines. And generally, we do not count that in our solution. But, with like a 5-line buffer, hey, you'd still have room to do that. But it's a lot less code to write if you just say, hey, I put the things inside of structure inside of curly braces, and I push back this set of curly braces, and it figures it out. It says, oh, you want me to initialize a structure from an initialization list? I know how to do that. It just happens. So that'll save you a little bit of grief if you remember that, and it turns out that this is a semester where that's necessary. We're still working on the final exam problems and getting them done, so it may or may not be necessary. Every coding question will tell you what you are or are not allowed to do. And so if you're allowed to use things from the STL, like for instance, if it says you're allowed to use whatever you want, well, we will put in a bunch of includes of basically the things we've used this semester. So we'll put in there, even if the problem doesn't need it, we've got a standard set of includes like, well, IO stream. Even if the problem doesn't require you to see out anything, we'll still include the IO stream just because it's a general thing. So we'll include IO stream, vector, stack, queue, DAC, unordered map, set, unordered set, just a bunch of things that are things that we've used this semester that are common, and things like algorithm and utility so that you have access to things like swap or min element or sort or whatever you might need. If you're allowed to use anything, we include it. It doesn't mean you can use anything. Maybe using one thing will put you over the time limit or put you over the memory limit. So just because it's there doesn't mean you have to use it. We just put the most common includes in there just to save you effort of putting it in there yourself. So the function header we give you isn't part of the line limit. Any includes that we give you are not part of the line limit. If you add includes, those are not part of the line limit. So includes are never part of the line limit, even if you add to ours. So it's basically the things that code the function or functions if you write a helper, but it's not the includes that get you the things you need, are not in the line count. For variable types, for integer types, we don't set the compiler to be super pedantic. And so if you say int I and I is less than vector.size, it should still compile. And if it doesn't, hey, we know how to read that. So if you stay consistent and use things that make sense, it'll be more likely to compile. And also stay consistent with what we give you. So if we tell you you have to return a vector of strings, then you've got to return a vector of strings. If we say return a vector of ints, you got to return a vector of ints. And so if you stay consistent with the data types that we give you, it'll reduce your grief. And if you're not sure which type to use an integer type that makes sense to you. And even if it doesn't compile, we can still read it and grade it by hand. Basically, if your solution compiles and passes all of the tests, then that just means it saves us some time. It doesn't mean if it doesn't compile or doesn't pass the test, that just means we have to look at it more closely. If it compiles and passes every test, then basically we have to make sure you didn't break any rules. That's all we have to do. But if it doesn't even compile, we will still give you every point that you deserve by taking time to look through it. That's coming up in just a few slides, Ojan. Like 3 slides, I think. We'll get there. So study materials, we've got 2 practice exams, 2 real previous exams. We've got other supplementary problems. The multiple choice supplementary problems were written by a student who was a student and then became a staff member, but wrote the multiple choice when they were a student, there's also a bunch of written questions. There's a bunch of written questions that don't have a semester, and there's a bunch of written questions that do. The ones that do are ones that we, the staff, wrote and had, 20, 40 people editing them. The ones that don't list a semester, I don't really like to answer questions about too much because there's too many of them. I don't know them well. And like I said, they were written by one person. And one person might have written an ambiguous question where it's like, wow, if I think of it this way, this is the right answer. And if I think of it that way, that's the right answer. The ones that were written by one person might not even have the right answer marked as right. Hopefully they do, but it's not guaranteed. So they're great to think about. They're great to use as like tools for discussing with other students, like how would you solve this? But they're not necessarily perfect answers to them. And even our own exams aren't perfect. Like there's an exam question that has a comment in it that says, this isn't the best question because we didn't say whether we wanted worst case analysis or average case. So, excuse me. So the questions that we wrote that are the real exam questions are a bit better and better edited. So other things, lecture slides and recordings, you can use to study in-class exercises. The written exercises that you did are all good practice. We had you do those for a reason because they help you think about coding. So studying with other students and tossing around like, hey, there's too many of those real written questions. Just even if we just stick to the real ones, not just the supplementary writtens, but just the real written questions, there's too many for me to write all of them. So how about I get together with a couple of other people I know and we'll each pick 3 of them that we'll write, and then we'll sit down for an hour and discuss each of them. So topics. So cumulative. So everything is fair game, but we tend to focus on the things since the midterm. So that doesn't mean we won't ask you about things like a solution that might need a vector. Pretty much many of our written problems have a vector involved, right? So we have to give you a collection of data. How do we give it to you? Usually in a vector. But we could give it to you in a queue. Maybe a queue is required to write the solution or a stack. Maybe a priority queue is used to write it. So it'll be all things that you have used a fair bit. If it's needed for the solution, you have used it. But we are going to tend to focus on things since the midterm. So we might ask you things about complexity of trees and hash tables. We might ask you about complexity of shortest path or algorithm families. But we're not going to say, here's a recurrence relationship, solve it. But we will ask you questions that involve the complexity of things since the midterm. And you will have to take the complexity of the things into account when you write a solution. So strings and sequences, which we just covered, is on the exam. The computational geometry is not on the exam. And the reason for that is that it tends to make questions that are either really hard or painfully obvious. And there's very little middle ground on questions we have been able to write in the past. We've asked staff members to write them, and they've written questions that were usable, just they weren't a good range of questions. We didn't get enough of them, and their difficulty level varied too widely to use. Okay, so the next part is topic review. What I'm going to do is I'm going to pause here, and I'm going to switch over to my PDF editor. And this will probably goof up when I switch over to the practice exam. Yep, it always crashes when I start it and it's already open and stuff. Okay, so now I don't need a new version. Exams. So this is the final practice combined. It says -2, but that's just because I downloaded 2 copies of it because I knew it was going to be. I downloaded a second copy because I changed one thing in it. So what I'm going to do is I'm going to skip to page 17, which is the first of the written problems. Now, this one I just noticed when I was getting ready for lecture. I noticed that when I added, so our file used to have, like, hidden from you the bottom-up solution. And what I did was I added a top-down solution, but I goofed and I didn't put it inside of the LaTeX code that hid it. So when you looked at the question, you could have actually seen the answer to the top-down solution. Now, we have a PDF that's going to reveal at 12:01 p.m. that has both answers. It's got the top-down solution, it's got the bottom-up solution, and they're both in there. But I edited this one so that the solution was hidden while we're talking about it. So the order of the problems doesn't matter. It could be 25, it could be 26, but there will be a dynamic programming problem on the exam, and it will say dynamic programming. Either in the title of the problem or the line just below it, it will say, and it'll even be underlined, it'll say, like, this is a dynamic programming problem. So dynamic programming problems are hard enough without wondering whether this is the one. So the dynamic programming problem will say somewhere that it is dynamic programming. So let's talk about, before we get into this problem, let's talk about how to solve DP problems in general. So, like any problem, you have to understand the problem before you start coding. You have to start understanding how you would solve it before you start coding it. If you can write a recurrence relationship for the problem, then you can code it. So it's good for recurrence, for DP problems. It's not required to write a recurrence relationship. I would either write a recurrence relationship or draw out a diagram, like, for example, with the Lab 10 autograder, the meal punches question. That one is one that, yeah, you could write out an equation or you could draw it out and understand it, but you've got to have something other than code before you start coding. So start understanding the problem. Look at the requirements. The requirements tell you things about the memory. It tells you things about the memo. It tells you things about the complexity of the solution when you're done. And it could tell you things about how you have to solve it or what data structures you have to use. So in DP, we're going to be putting things in here, etc. But if in any problem you see the word average, so you have to hit a certain target average complexity. Why would we say average? This is a good question for you. Think about it. I'll come back to that in a minute. Type answers into the chat window. What would average mean to you in terms of what you might need to use to solve that problem? Okay, so then if we understand the time and memory complexity, we can start to understand what the memo will look like. Now, the Lab 10 is a good example of where the requirements can be slightly misleading. So like the Lab 10, the memo is complexity of the memory is linear. That doesn't mean it's a one-dimensional, though. In Lab 10, it was a two-dimensional memo, but one of the dimensions was fixed at size 6. So it can be informative, but it's not necessarily the only thing that goes in there. So Lab 10 is a good counterexample in that respect, in that we needed a two-dimensional memo, but the requirement was really O of n because one dimension was fixed at 6, and that was part of understanding that problem. So understand the problem, understand the complexity will get you what the memo looks like. Once you have what the memo looks like, then the real key is how is this thing in the memo related to two or more other things in the memo. Now, there could be base cases where, oh, this thing is a base case because I can figure it out easily, or it's only related to one other thing. Or it might be like an edge case. But generally, if it's DP, something in the memo is related to two or more other things in the memo, because If it was always this thing is related to one other thing, then I don't need DP. I can just loop and keep track of which value I need as I calculate it. Done. So if every value is related to one other, we don't really need DP. We need DP when one value is related to two others in the general case. Like I said, there could be edge cases where it's only related to one. There could be base cases where it's related to nothing, but most of them will be related to two or more other things. Okay, so what this problem says is we want to tile I want to make sure I'm going to look at my preview and see if, okay, I'm not scrolled badly. All right, so we need to tile a 2x(n) board. Now, when we gave this problem, some students misread it. They thought it was n/n, and they were lost. And that's n/n for this would be a much, much more complicated problem. So this one's enough as it is with 2x(n). So it's always 2 rows, but the number of columns is n, and n is greater than 0. So I'm interested in the number of distinct ways. We'll get back to distinct in a minute. Oh, and I forgot to look back at the chat window to see what people said. People didn't say. So if I said average case complexity, what does that make you think of as a potentially important data structure? Would be hash tables, because hash tables have average case O of 1 lookup. But they could be worst case O of n, which might make my complexity, instead of average case something, it might make it worst case n times that. But the average case would be the thing that we stated. Okay, so this one. So we said the number of distinct ways to tile the given board, so we'll get back to the distinct in a minute, and we're allowed to use tiles of dimensions like these. So these are the 3 shapes we're allowed to use. And if you want to, you could think of them as having like slightly different patterns on them, even though they're different shapes. Like this one has dots on it, this one has slashes in one pattern, and this one has slashes in that pattern. Or maybe it's crosshatched. Okay, so think of it that way. So you can tell the individual pieces apart when you look at a board. So if we said the board is size n is 1. So if n is equal to 0, let's go to 0. If n is equal to 0, how many ways are there to tile the board? There's one way to tile the board. Pick nothing. All right, what about when n is equal to 1? When n is equal to 1, there's one way to tile the board, and it looks like that, the vertical piece that has the dots in it. It looks like that. So then, if I say I want you to tile a board where n is equal to 2, well, I could solve an n equals 2 board by picking one of the big 2x2 tiles. I could pick 2 2x1 tiles and put them next to each other. And we showed the gray here just to distinguish between these and the 2x2. So we've got 2 vertical ones side by side, or we've got 2 horizontal ones on top of each other. So that's what we want to do. And we'll get to the distinct in a minute. We'll try to work on n equals 3 and how many ways there are to tile a board of size 3, and that'll give us our hint on the how to build up the larger cases. All right. So what if, and I'm going to have to either draw this. I'll draw it up in the corner here. So let's say we do n equals 3 over here. And I'm going to have to do this maybe a little bit smaller, but we'll get it done. Okay, so n equals 3. So I could start with a big one, the square one, and then add a vertical one. Right? That's one way to do it. I could start with 2 vertical ones and then add a third vertical one. I'm going to show it a little bit of separation. Really, they'd be next to each other, but I could tell them apart. But I could see that there were 3 vertical ones there because the vertical ones have the dots on them. Okay, that'd be another way. I could start with 2 horizontal ones and add a vertical one. Okay, so that gives me 3 ways so far. But what if I had started out with 1 vertical one? If I'd started out with 1 vertical one, I could add a big square one to it. If I started out with 1 vertical one, I could have added 2 vertical ones next to it. Or if I started out with a vertical one, I could have added 2 horizontal ones next to it. So it looks like there's 6 ways to get there. But when I look at it, these 2 look the same. Because when I tile it, I really do put them side by side. But I see 3 in a row that have polka dots. Now, whether I put down 1 and then put down 2, or put down 2 and then put down 1, doesn't matter. I can still see that those look the same. So that's where the distinct comes in. Now, if you got this problem in the semester we gave it, if you got this problem completely right, and except for the distinct, it was like 1 or 2 points off. So it wasn't a huge amount, but it was in there that we wanted people to notice that. So for n equals 3, there's actually 5 ways to do it. Now what we need, like I said, is a relationship. How is t of n related to smaller ways? And t here is the number of tilings, right? So if I say, hey, I want to write down the number of ways to tile this. So the number of ways to tile this, I'm running out of places to write things here, so let's put it here. So t of, we can do base cases. Hey, let's do base cases. Those are easy. T of 0 is equal to 1. T of 1 is equal to 1. T of 2 is equal to 3. Hey, we gave you those. And you could actually use, if you get the formula right, you could use these 2 as base cases, or you could use those 2 as base cases. It doesn't matter. As long as your formula is right, you could use either one of those sets of base cases, or you could use all 3 as base cases, I suppose. But you really only need 2 of them, because we did say when we give you the solution, n will be greater than 0. Okay, so we need a relationship for t of n. So when n is arbitrarily large, t of n is how many ways are there to tile a board of size n? Well, that's equal to the number of ways to tile a board of size n minus 1, and then I add a vertical one to it. So that's like, this is basically the top row. So the t of n minus 1 is the top row. It's saying, take what you've got and add a vertical one. There's only one way to do that. So you get however many ways there were at t of n minus 1, you take that number, and that's how many ways there are to tile this one if you add a vertical one. Okay, or we could add some number, we'll get back to it, some number times t of n minus 2. Now, if we put a 3 there, we get those 2 that look alike. So if we put a 3 there, we get the 2 that look alike. If we put a 2 there, we get rid of the duplicates. So that allows me to get to the vertical ones in a row. There's only really one way to do the vertical ones in a row, is do the vertical ones and then add one more vertical one. Now, this is the hard part of this problem to see. If you put, like I said, if you put a 3 in there, you got most of the points, either 13 or 14 points if you put the 3 in there. But 2 is the right answer to eliminate the duplicates, to eliminate the 2 right here. Instead of getting 2 of those, we only get 1. All right, now once I've got that, I can write a solution. So once I've got that relationship either written down either as a formula, or I could draw it out. I could say, hey, in my memo, I got this one. Okay, this one at index I is related to this one at I minus 1, and this one at I, so that's I minus 1, I minus 2 times 2. So I take this one plus that one times 2. And so I draw it out, and from that drawing it out, I can write the code for it. So I can write it in terms of I can write it in terms of n, it doesn't matter. The variable is not what's important, the relationship is what's important. Okay, so now we've got to write this. Like I said, accidentally the top-down solution was already there visible. So let's work on the bottom-up together. And when the answers auto-reveal, both of them will be there. But let's work on the bottom-up solution. All right, so if I make I need a memo. I need to keep track of the number of each one. So I'm going to need a vector, and it's in there. I'm allowed to have an auxiliary space. Okay, let's put in a vector. Vector of, well, I could make it a vector of integers. I could make it a vector of size t's. I'm supposed to return an integer, and since I'll be grabbing something from the memo to return, let's make it a vector of integers. Because I'm supposed to return an integer, let's make it a vector of integers. Okay, and then we could give this any name we want. I think in the example we called it memo. Okay, and then I'm going to pre-size this vector up front and save a line of code doing it. I'm going to say I need a board of size n plus 1. Now, wait a minute. How did I know it was n plus 1? Well, one way I know is that I have to return t of n. I have to return a tiling for size n. And it would be convenient if when I wrote the code that the size of the board corresponding to the index. So whether I want these two base cases or these two base cases, well, if I want the t of 0 and t of 1 base cases, I need the memo to be size n plus 1. If I do the t of 1 and t of 2 base cases, I could have a board of size n, but then a board of size I would actually exist at index I minus 1. And that could be confusing. It could cause me to get the code wrong. So for this one, I'm going to make the memo size n plus 1. The index indicates the size of the board, and it allows me to look up the last element that I need. I need a board of size n, and so then I want the n to be at index n. I need a memo of size n plus 1. Now, when you resize or pre-size a vector, by pre-size I mean, hey, I put it in the declaration. I put the size in the declaration, it is created and sized at the same time, and by default, it is initialized to all the default values for that type, which for integers is zeros. If it was strings, it would be empty strings. If it was Booleans, it would be all false. So the nice thing is vectors, when you new an array, you don't get default values. But when you pre-size or resize a vector, you do get default values. Okay, so that gets me the initial size. And then unlike arrays, here's the downside, unlike arrays, I can't put the equals curly braces in there at the same time. I can do one or the other. I can either resize it or I can give it initial values for some elements, but I can't do both. So I need a few lines of code here. So I got to put in my base cases. So I can say memo sub 0 is equal to 1, memo sub 1 is equal to 1. Oh, let's put some semicolons in there. Okay, so I've got my memo initialized. And now I can run a for loop. Run a for loop. For. What was I given? So n is an integer. So I was given as an n as an integer. I'm going to compare to n. So let's make my for loop variable be an integer. Int I is equal to, wait, not 0. That's a typo. Undo. There we go. I equals, so I've already got 0 and 1 are done. I want to start out at I equals 2. Okay, so I started at I equals 2. I'm going to run as long as I is less than or equal to n, and I'm going to increment I all the way through. Okay, so I'm going to run through everything I need from bottom to top, from smallest cases to biggest, and then I can say, well, memo sub I is equal to, memo size I minus 1 plus 2 times memo, that's an ugly 2, 2 times memo of size I minus 2. And that's it. I don't need any other lines of code, so I don't need curly braces. If I put curly braces, it doesn't count against my line count anyway, so I would do whatever my IDE does. So if my IDE puts in curly braces by default, then I'd probably leave them there. Okay, and then when I'm done, I can return memo square brackets n, or alternatively, I could say memo.back. That takes more characters to type. 6 characters, 7 characters versus 3. Let's go with square brackets n. And then curly braces to end the function. So that's all it takes to solve this one. Really, the hard part I would say is the understanding. Getting that relationship down is the hard part of this problem. I haven't been watching the chat too closely. Okay, yep, nothing in there. I was just keeping an eye on my preview to make sure I was in the right, keeping my PDF editor centered properly. Okay, so for this semester, that was the DP problem. Now, it turns out, as we were grading this, one of my staff members, who was also getting a math minor, we're in one of the lecture halls, we're grading, and he says, I think there's a closed form solution to this. And he goes up to the whiteboard and he works out this complicated closed form solution, meaning it didn't need any loops, didn't need a memo, but it was really complicated because it was like, if it's odd, if it's this way, if it's even, it's that way, and solved it, and it coded it up, and it gave the same answers. And then later on, while we were grading, a student who was taking the exam came up with a closed form solution that was even cleaner than my staff members. He discovered that integer arithmetic took care of the even and odd cases, and done. So we didn't realize when we wrote this one that there was a closed form solution. Generally, there isn't. If you think there's a closed form solution and you bet all your points on that closed form solution being right and it's wrong, you're going to lose a lot of points. So I would say, hey, write it. If it says it's DP, write it as DP. If you're right, hey, put it in the comments. Put a closed form solution in the comments, and we'll look at it and we'll be impressed. But don't go for the closed form solution unless you are absolutely confident. But generally, there is not a closed form solution to these problems. This was a real rarity. This is the only one that we've ever given that was a DP problem that had a closed form solution. Okay, so like I said, in the solutions, there's the top-down solution is in there, the bottom-up solution is in there, and it also, I think I've got it loaded somewhere here. Different window. Yeah, and ours has a few different comments in it besides that. And it also, the comments also have they have the recurrence relation in there, and we wrote it in terms of like f of I instead of t of n, but it's the same thing. It's a recurrence relationship. And it's got some comments and explanations. It's got the top down and bottom up. Okay, so let's go to a new page and new problem. Okay, so this was an unusual exam. It was an unusual exam in that it had 3 coding problems. It had a DP that wasn't terribly long. I mean, if we look back at our solution here, the bottom-up solution is 1, 2, 3, 4, 5, 6 lines of code. And what was the limit? The limit was 12, which was double this. So I think the top-down solution ended up using a few more lines of code. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so the top-down took 9, the bottom-up took 6. 12 lines were allowed. Okay, so this one was unusual in that it had 3 shorter coding problems. So this one is, we've got a node structure, so we gave you that up front, and we said you have to implement the exists function. So this, we didn't want to make it hard. We didn't want to make it a member function and a root pointer and stuff like that. this could be a private member function. The public member function gets passed just a value. It calls the private member function, which accepts, say, root and the value. So this one you have to write the one that accepts a node pointer of, hey, here's where I am, and a value. Now this one, I'm pretty sure so this one there's no solution visible there, and I'm pretty sure, let me page through my actual solution document. Yes, we did have both solutions in there. So this one can be written with recursion, or it can be written iteratively. How do I know, looking at it, that I could do it either way? It says in the average case, your solution must be O of log n. So here's one where average doesn't mean you need a hash table. Here, average means that if I did a recursive and somehow it was not tail recursive, I would still be able to have that average case stack space of log n. Average case meaning it's the average tree is not a big stick. So that's why average is in this one. So average doesn't always mean hash table, but it could mean that, hey, you're doing binary tree stuff and the average tree is branchy. It's not stick-like. Okay, so it says in the average case, your solution must be O of log n, and you may, the average case, so that means, so the average case here must be log n, means if it's tree-like, which is the average case. So the average tree is tree-like, your solution must be O of log n, and you may use up to O of log n auxiliary space. That was basically the call space for a recursive solution that is not tail recursive. The one that we gave you is tail recursive, and most people who wrote it did write a tail recursive solution. So we can write this one either way together, but the answer that's going to auto-reveal is going to be both of them. So we can do it either way. So I think students are less comfortable with recursion, so let's do the recursive solution together. So this one's not too bad. We've got a binary search tree. We want to know if the solution is in there, and we're going to write a recursive solution together. So if this is a recursive solution, I've got to have a base case. I've got to have a base case of if node is equal to null pointer. Or alternatively, I could say if not node. Either way works. Write it the way you're comfortable with. So I say if node is equal to null pointer, or if not node, then I know I've reached a null pointer. So I was going left, right. I was looking for 9 and I found a null pointer. I can return false, because I didn't find it. I searched the right way every time, but I reached a leaf node and I got a null pointer off of that leaf node. So I don't look for a leaf node, but I look for, hey, somebody called me with a null pointer. I've run out of places to look. All right, so that's a base case for our recursion. You could think of it as another base case, but what about if it's not a null pointer, what if I found the value? That's kind of like a base case, right? So if node arrow val, a val, right? Yep, okay, so that's the name of the member variable is val, and the name of the parameter is val. So if node arrow val is equal to the value I'm searching for, then I could return true. I did find it. So I got all the way down to the bottom and I found it. All right. And it's safe to do that because if it was a null pointer, I would have already returned false. So I know it's not a null pointer. It's safe to use the dereference arrow. Now you could write this as dereference node dot val, but it's harder to read and it takes more characters to type. So it's a lot easier to do with the arrow here. All right, so that tells me that I've got a base case, I found it. Okay, well, what if, so now I need an if to know whether I should look left or whether I should look right. I like to do left first. The order doesn't matter because it's going to be in one of those subtrees if it's there, and we got a 50-50 shot, so the order really doesn't matter, but most people, at least English speakers, like to do left to right first? That's an interesting question. If your native language is Arabic, do you like to look at the right subtree first? That's a good question. If someone's native language is Arabic, I'd be curious to know the answer if that's your go-to solution is right to left. Okay, anyway, or if you're left-handed. Maybe if you're an English speaker but you're left-handed, you like to go in a different direction. Or maybe you just like left first because you're left-handed. Anyway, okay, so I want to know if I need to look left. So if the value I'm looking for is less than what I'm looking at, I should go left. So if the value I'm looking for is less than the value I'm looking at, then I can call exists on the left subtree. Almost. I can call exists on the left subtree, but I have to return whatever it returns. So when I make my recursive call, return exists of, okay, so now I've got to call it with the left subtree. So that would be node arrow left, double check my declarations, yep, node arrow left and right, and comma val. I've got to give it the value, whoops, val parenthesis. That looks like more. Okay, val parenthesis, there we go. Okay, so I can return exists of node left and val. Now I could put an else clause here or not, it doesn't really matter. I'm going to save a little bit of typing and just do a return. Return exists of node arrow right, comma val. So if I didn't already return from it being a base case or true or left subtree, then I can return the right subtree call. So I could do this with an else clause or I could do it with just a return. Doesn't matter which. All right, I think that takes care of it. That's the end of the curly braces there. So that should be everything that we need to get this done. We have two different recursive calls, but they are both tail recursive. Both of them can't happen because if one happens, the other can't. And as soon as a recursive call happens, this function can immediately return. So we have a function that is fully tail recursive. It has multiple recursive calls, but it's tail recursive on every possible path of execution. Therefore, it's tail recursive. So we didn't really need the log n auxiliary space, but it's there if we somehow goof this up and said like result equals exists of left, result equals exists of right, and then return exists, it wouldn't be tail recursive, but we'd still be within the limit. Okay, so that's that function. So that exists on a binary search tree based set. And it said the set wasn't really what's important. It was just that we had a binary search tree. We want to know if a value exists in it. All right, next one, blank page, code. Okay, programming, searching in a hash table. Okay, so we've got a hash table, so we've got an enumerated type status, and we've got empty, occupied, and deleted. This is kind of similar to the lab 7. So this is kind of similar to lab 7. Except it says, suppose the hash table implements the quadratic probing mechanism for collision resolution, blah, blah. And so the hash function, so you don't have to worry about a hash function. The entire hash function is val modulo m, where m is the size of the hash table. So we just have to do modulo whatever the number of buckets is. So there is one of the things to be careful of in writing this solution is that there is no m given to you in the function header. There's no m anywhere here. So when it says m, it really means the size of the hash table. We could, if we wanted to, we could make like a constant. Right? I could set a constant equal to the buckets.size, and then I could just use m after that. It would save me some typing. I could do that, but I can't write just m without creating m. excuse me, the requirements, it says your solution must implement quadratic probing. So when we did this, when we gave it as a real exam, that sentence wasn't in there. And students then tried to argue, well, yes, it said you were supposed to implement quadratic probing, but linear probing will still find it eventually. So when we turned this into a practice exam, we made it a must. So we really did, I believe we really did great at that. Like, people that argued that I did linear probing, therefore it'll find it even though it's supposed to be quadratic, we didn't give them full points for that. So when we modified it to be a practice exam, we put it in there as a must. Your solution must implement quadratic probing. Your solution must be O of n time. You may use O of 1 auxiliary space. So O of 1 auxiliary space doesn't mean you can only have one variable. It just means you can have a constant number of variables. You can't create a new container full of stuff, but you can create 2 or 3 or 4 or 5 variables as long as the number of variables does not depend upon the size of the hash table. Okay, now when you get the revealed solution, when I wrote this solution, I thought of it as hey, I've got to probe at least once. Since I've got to probe at least once, I wrote it as a do-while loop. But we found most students, that isn't their go-to solution. Most students' go-to solution is a for loop. So, since we're writing it together, let's write it together as a for loop. And if you want to look at the do-while solution, it's in there. The important thing is that, like Lab 7, we've got to make sure that we don't loop forever. So however we do it, we can't loop forever. We can't have the only way that my loop ends is I find an empty bucket, or I find that it exists. So we do want to stop when we find an empty bucket. We do want to stop when we find it, but we don't want to loop forever. If everything was either occupied with the wrong key, or it was, so if it was occupied with the wrong key or it was deleted, we don't want to loop forever. Okay, then the other thing we're going to need is, if we're going to implement quadratic probing, remember, we've got the hash, and we have to take the hash plus j squared. It's not our previous index plus j squared. It's not where we were previously. Like when I go from j equals 3 to j equals 4, it's not the previous index plus 4 squared. It's the original index plus 4 squared. And we always have to do modulo buckets.size, right? Whatever we do, we got to do modulo buckets.size. So I'm going to write this in, I think, let me think about how the solution, because I normally write this as a do while loop. So for loop, I'm going to need an index, but I can create that index inside of the loop. Yeah, we could do this. All right. So I don't even think we need any prep variables. I think we can just go straight into the for loop. Okay, so for loop, for. Now, the other thing about this one that was a little bit confusing to some students and we didn't take off points for it was, we thought this would be more confusing if we said this is a member function and buckets and status is a member variable. We thought that would be more confusing. So what we did was we passed the hash table as a variable. The hash table is a struct. Everything in it is public. So you can't just say like buckets.size. You have to say tbl.buckets.size, tbl.status, etc. So you've got to say tbl dot. So that was one thing that some students had trouble with doing, was they left all the tbl off. And we realized, hey, we made this more confusing by not making it a member function. So we didn't take points off for that. So for, I need an index here. I know that I'm going to compare it to a size and of a vector, which is a size t. So let's make it a size t. Size t. J is equal to 0. J is less than tbl.buckets.size. plus j. Okay, so that's my loop. I'm going to run through every possible j, but I'm not going to loop forever. I'm going to stop when I've looked at all possible j's that make sense. Okay, then I'm going to figure out I need an index, size t. Let's just call it IND for index. Index is equal to, so I've got to do the value and I've got to do modulo m. So really the value is the index. So if they give me a 57, I should go to index 57, but I've got to do it modulo the table size. But what I need here is I need value is really think of it this way. The translation of a key is equal to key. The compression of of the t of key is equal to t of key modulo m. So the compression is just modulo m. So I always have to do compression. So the translation is the value itself. Or I could have said t of val is equal to val. Maybe it would have made more sense. So t of val is equal to the value. All right, so I need val plus j times j. So that's my plus j squared modulo tbl dot buckets dot size. Now, could I take the value modulo table bucket size and then add j squared and do the modulo again? Yes. Would I get the same answer? Yes. So the order doesn't matter. As long as the whole thing is moduloed, I will get the right index. So whether I do value modulo m and then add j squared and do the modulo m again, or whether I do the modulo m once, I'll get the same answer. Okay. So that's my index. So now what I've got to check is if I'm done. And I could check, I could look and say, hey, if it's empty, I'm done. Or I could say, if this is the right one, I'm done. Doesn't matter which I check first. I got to check both. So let's do, I would say students probably want to go for, I'm done because I found it. So let's do that one first. So if, and I'm going to indent here a little bit because I like my ifs to line up nicely. So if it's occupied, so that's tbl dot status sub ind, not j, but index. If tbl dot status sub index is equal to status colon occupied, and the value matches. So that would be tbl.buckets, b subindex is equal to the val I was passed in. So if both of those are true, then I can return true to say I found it. Oops, TRUE. Okay, so, but there's no else clause. I could do an else clause, it doesn't matter because if it was true, I would return. I could do it as an else, or I could just do another if. If I find an empty one, if tbl dot status at that index is equal to status colon empty, it's never held anything, then I can return false. Because I might have probed, quadratic probed, because I kept finding occupied empty ones, or I found deleted ones. Either way, I found occupied ones with the wrong keys, or I found deleted ones. I just kept going, and then but when I find an empty one, I can stop immediately. So if that's true, I can return false, And otherwise, I just let my for loop keep going. So if it was occupied with a different value, if it was deleted, I would just keep going. But then when the loop is over, so that's the end of my for loop. But if that gets out of that for loop, I've got to return false because I got a bunch of either occupied with the wrong values or deleted over and over and over. Occupied, wrong value, deleted, deleted, occupied, wrong value. Never found it, looped n times. I got to give up and return false. It's not in there. And then that's the end of the function. Now, you don't have to comment your closing curly braces. I do just to keep them straight. So that if I end up missing a curly brace, I know who I forgot. But you don't have to do that. Okay, so we've got that one. Like I said, that one's all written up differently. The one that I wrote in the solutions initially has a do while loop rather than a for loop. And my do while loop basically loops until I get back to the start index. So I had like a start index and I had my current index, and I said, well, my current index is equal to, initially it's equal to my start index, and then all the way through I said index equal to my start index plus j squared modulo the table size. And if my index that I'm at ever gets back to my starting index, then I stop because I've come all the way around and I'm starting to duplicate effort. So either way was valid. You just had to make sure that you didn't accidentally loop forever. Oh, I haven't been keeping track of, where's my live stream window? Okay, haven't been keeping track of questions, but Professor Darden's here for that. With the quadratic probing, remember we talked about in the lecture in quadratic probing, we talked about the residual squares, where when you take integer plus another integer squared, modulo anything, there's only a limited number of possible values. Either way, either loop n times or loop until you get back to the starting point. It's a good question. Does it hit all of them? The thing is, it hits all the places where it could have been, right? It hit all the places where it could have been. That's the important thing, is that it hit every place where it could have been. And it will be, as long as you keep quadratic probing below 50% full, you won't have the problem. So residual squares only becomes a problem when you get more than half full. So as long as you keep your load factor at 0.5 or better, you'll never have this problem. You'll never have to worry about it. Okay, so that's it for the practice exam 1 writtens. Let's go back to the PDF, and hopefully it'll return to right where we left off. Wait for my preview window to catch up. Okay, there we go. All right, so this is where we were. So, trees. So we're just going to go through topics, and I put them slightly out of order here. I put trees first because it makes more sense to do trees before hash tables. Just during the semester, we had to do hash tables first because we really needed them for Project 3. So, for example, we had general trees, binary search trees was adding a rule. We had AVL trees where we added another rule. So, to get from a binary tree to a binary search tree, we add a rule about small values go left, big values go right. With an AVL tree, we add another rule that says no node is allowed to have a balance factor greater than 1 or smaller than -1. And if we impose that and keep it consistent throughout, we get a balanced binary search tree using AVL trees. So we had an example problem here, and we don't have a full solution to it, but we've got a bunch of values and we've got one of the many views of how to do rotations. And so it says insert these keys into an AVL tree, rebalance when necessary. So let's do a few of these together. Right? I've got a blank slide in here next. What we need to remember is the 4, 2, 3, 5, 7, 4, 2, 3, 5, 7, 4, 2, 3, 5, 7. Oh, I know. I'll put it in the chat window. 4, 2, 3, 5, 7, 8, 9, 13, 12, 10. All right, there we go. Now I got it. Okay, so we want to insert in that order. So I insert 4. Okay, 4 becomes my root, no problem. All right, then I insert 2. 2 has to go to the left of 4, no problem. Still balanced. Everybody's balance factor is 0 or left minus right is +1, so we're good. Okay, then I add 3. 3 must go to the left of 4 to the right of 2. And now we got a balance factor problem. So let's write down the balance factors. New leaf node is always balance factor 0. Work our way up the tree. Remember, as the recursion unrolls, we check every level that was part of our insertion path. This one has a balance factor of 0 minus 1 is -1. This one has a balance factor of height of 2 on the left minus a height of 0 on the right is +2. Hey, that one's out of balance. That one's out of balance because it's a +2. We look left, we see a negative number there, which means we need a double rotation. So when I do these, I always write down what's happening. I need a double rotation. I want to rotate right at 4, but before I do that, I must rotate left at 2. So I'm going to write those down so I don't forget that I'm in the middle of a double rotation. Okay, so that's what I have to do. So let's do the rotate left at 2. Produces a tree that looks like this. 4 goes to 3, goes to 2. Check, that's done. Now I've got to do a rotate right at 4. Okay, and that produces a tree that has 3 at the top, 4 moves down and right, 2 stays in the same relative position to 3, and we're back in balance. Now, here's a trick. A perfectly balanced tree, which this is, you can do at least 2 insertions before you have to worry about rotations. Just like when I had an empty tree. An empty tree was perfectly balanced. I know I can do at least 2 inserts. Hey, I've got 4. 4 is perfectly balanced. Back when it was just 4 and nothing else, 4 is perfectly balanced. I know I can do at least 2 more insertions before things get out of balance. Could do more. You know, if my insertion order had been 4, 2, 5, I wouldn't have needed any insertions yet. And then I could have done at least 2 more. So I'm at 3, 2, 4. I can do at least 2 more insertions before anything goes astray. So let's change colors again. So I can insert, what's my insert? Next is 5. 5 goes right of 3, right of 4. That's fine. Then we insert 7. 7 goes right of 3, right of 4, right of 5. 7 goes here. And now let's check balance factors. Looks out of balance to me. Okay, so we got a balance factor of 0. 0 minus 1 is -1. 0 height on the left minus 2 height on the right is -2. We are out of balance. We've got a -2, so we look in the right subtree. We see a negative number there, so we don't need a double rotation. We just need a single rotation. I just need to rotate left at 4, and that gives me the tree 3, 2, 5, 4, and 7 stays in the same relative position. 4 and 5 changed roles. What if 7 had, what if 5 had a left child? Where would it have gone? If somehow we got to the point where like 5 had a left child, well, if 5 had a left child, like it would be something like 4.5. 4.5 would end up as 4's right child. If the values are unique, it's easy to predict where it ends up because there's only one place it can be and still be a valid BST. But think of it this way. If 5 had gained a new left child of 4, its old left child would have to go somewhere else. 4 lost a right child, it has room for a new right child, which would have been 5's old left child. So when you get into a more complicated case, we couldn't do that with a tree this height. But with a more complicated tree, we could get there where we needed someone had to change sides and roles. Okay, so there's a few more here. You can do it on your own, and you can go back to like Visual Algo and look at it. Okay, hashing. So we did hashing functions. We talked about different ways to hash things. We looked at how we do a hash table. We looked at collision resolution techniques, separate chaining, and all three of these, which have the same category, open addressing. Now, beyond that, is it in the slide? It's not in the slide. Should have put it in here as another bullet point. Dynamic hashing. That's when you have to grow the hash table. And growing the hash table is an independent of the collision resolution. No matter what your collision resolution technique is, you need dynamic hashing. You should have a way to grow the table. Now, the one that's in Canvas files sample code, the one that's in there, that's the separate chaining, does not grow. It always has a fixed size table underneath, and it doesn't do a rehash and grow. Why? Well, partly because we left that for you on the lab. So really, the implementation there should be more complicated. It shouldn't have a fixed size array. It should have a vector. The vector should grow. It should keep track of a load factor, know when to grow, have a rehash and grow function, etc. Okay. So when we say, hey, what about our complexity here? If we've got a hash table and we want to add things to it, then what is our complexity? What if it's separate chaining? What if it's linear probing? What's our best? What's our worst? What's our average? Now this one is there's one in here that's slightly unfair. The average linear is pretty complicated. That's the one where we said you didn't need to know it for the exam, but that's why this is a review question, not a real exam question. So for both of these, the best and the worst are pretty easy. Right? The best and the worst is O of 1. Or sorry, the best for both of them is O of 1. So the best for both of them is O of 1. The worst for both of them is pretty easy, O of n. Right? The worst case complexity is O of n. If we get a lot of collisions all in the same place, either they're all in the same linked list in separate chaining, or they are all in the same cluster in linear probing, we could get as bad as O of n. Even if our hash table was only half full, they could still all n out of the 2n could all be together in one cluster. We could get unlucky. Now the average case, AVG, average case here, for separate chaining would be O of n over m is equal to, that's supposed to be an m, equals O of alpha, the load factor. We'd like it to be proportional to 1. We'd like to keep our load factor at 0.5, and therefore our average lookup time is constant. Now, in linear probing, we want our average to be constant, and we want our load factor to be less than or equal to 0.5, but the actual formula is that complicated one in the slides involving the 1 over 1 minus, or 1 over 1 minus 1 over 1 minus alpha or something like that. It's complicated. But we know the goal. The goal is to get a constant time, and we know that we get there by keeping the load factor reasonable and not getting terribly unlucky. So the average case assumes that we don't get terribly unlucky and get collision, 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 collision. And we can, even if we do get good behavior, we don't get a lot of collisions. If we don't control the load factor, we don't get a good average case. We don't get constant average case. Okay, graphs. So we talked about graphs in general. We talked about a bunch of terminology and types of graphs. We looked about adjacency matrix and adjacency lists. We looked at depth first search and breadth first search. We discussed the MST algorithm, or actually the MST problem, and two different algorithms, the Prim's algorithm and Kruskal's algorithm, both of which are greedy. And we looked at shortest paths with Dijkstra. Floyd-Warshall's in there, but you don't have to know it. We didn't cover it. But a bunch of terminology. Wait, I've got to remember someday to go and modify these slides and take degree out of there. We never actually talked about degree. Degree is the number of edges connected to a node, but we never really talked about degree. It's a standard graph theory term which we never actually defined. So skip degree, don't worry about that. But weighted graphs, we talked about when is a graph dense, when is it sparse. There's no hard and fast line between sparse and dense. So we said here E is much less than V squared. Alternately, we could say that E is proportional to some constant times V. That's the same thing as much less than V squared or constant times linear. So we talked about simple paths and we talked about simple graphs. Remember we said that a graph is simple if we don't say otherwise. You can assume it doesn't have parallel edges, it doesn't have self loops, like A is not connected to A. However, if it is a directed graph, that's still a simple graph. When it's a directed graph, A can go to B, B can go to A. There's no duplicate edges there. There are different edges in different directions. There's an edge from A to B, there's an edge from B to A, but it's still a simple graph. Now we talked about a bunch of different graph problems. Traveling salesperson, you're very familiar with now, hopefully from Project 4. We talked about graph coloring. We talked about the knapsack problem, the N queens problem. We did the night tour problem as a DP. It's kind of related, but it's a counting problem rather than a constraint satisfaction. So we didn't do backtracking for that when we did DP. So we've got an MST here. We said, hey, here's a graph. Do prims and Kruskals on this graph. So how would we do it? Well, prims, hopefully you're pretty good at now after Project 4 Part A. So how could we do Kruskal on this graph? Well, we could write down all the edges. We could sort them. We could then go through them in order. But that would take a lot of work. What I could do is I could start circling things and crossing things out. As long as I don't make any mistakes, I'll do all right. So I could say, hey, I've got to Kruskal this. Edge of length 1, I'll take it. Doesn't produce a cycle. These are in. Those are connected. Edge of length 2, I'll take it. That one's connected now. That one's in. Edge of length 2, that one's in. I still haven't produced any cycles. Edge of length 3. Don't have any edges of length 3. Edge of length 4. I see one. I'll take it. It doesn't produce a cycle. Those edges or those vertices are in. That edge is in. And now I've got a forest, right? Kruskal is building one part of the graph that's connected, another part of the graph that's connected. They are not yet connected to each other. Okay. How about an edge of length 5? I see one of them. Can I grab the edge of length 5? Well, it doesn't produce a cycle, so sure. I'll grab that edge. E is now in the graph. Okay, edge of length 6. I see one of them. Ooh, edge of length 6, that produces a cycle. Nope. Edge of length 7. I see one. That produces a cycle. Nope. Edge of length 8. I see two of them. I can include one of them. I can't include both. The first one I saw was the middle of the graph. Let's pick that one. And that one's in. And now the forest has become a single tree. The two subgraphs are now connected. Other edge of length 8, I can't take it because that now produces a cycle. Edge of length 9, I saw the one on the left first because it was next to the 8 I just crossed out. That one would produce a cycle, right? Because they're not just edges, they're not just vertices that are connected, they're connected to each other. So I can't take that 9. I can't take the other 9, that would produce a cycle. Can't take the 10, that would produce a cycle. And that's all the edges I'm keeping. So there's my MST. Oh, wait, I chose a slightly different one. So I chose that 8. The solution here chose that 8. But you could do either one. You get equivalent MSTs. They have the same total cost, but they choose different edges. And remember, on the autograder, when you turn in Project 4 Part A, it'll grade it correctly either way. It'll just make sure you have a valid MST. So we've got an outline of Prim's algorithm. I kind of want to get done here since we're a few minutes over. So we hope you know Prim's algorithm by now. Kruskal's algorithm, Dijkstra's algorithm. So Dijkstra's algorithm solves shortest paths. Dijkstra's algorithm is almost identical to Prim's except for the cumulative sum. It's not what is the weight of this new edge, it's how long did it take me to get to the current vertex? What's the cost to get to the current vertex plus the cost of the new edge I'm considering? So the recorded information is almost the same. And, oh, Dijkstra's starting at node A. I think we're out of time for this one. Do this yourself. And what I'm going to do is I'm going to show you the solution. Later on, come back to this, run through it, pause the video at this point, run through it, solve it yourself, then unpause it and look at the solution. If you're live now, close your eyes for a second. I'll tell you when it's safe to open them. Okay, so there's the solution. We'll get that up for a couple of seconds. And I said starting at A is the one who has a distance of 0, and then move on to the next slide. Okay, it's safe to open your eyes. All right, so algorithm families, we talked about the different algorithm families: brute force, greedy, divide and conquer, dynamic programming, backtracking, branch and bound. And brute force is a simple, in quotes, way. Brute force isn't always simple, but sometimes it is simple. It is always straightforward, but it's usually terribly inefficient. Greedy, the key about greedy is you make the best decision you can make right now, and you never reconsider a decision. Once it's made, it's made. You choose the best thing right now that doesn't violate any constraints, and you never look back. Are greedy never optimal? Well, greedy are sometimes optimal. Prim is greedy, Kruskal's greedy, Dijkstra is greedy. As long as you follow the rules of Dijkstra, no negative edge weights, Dijkstra is greedy and optimal. But if you were to give Dijkstra negative numbers, things change. But some things are never optimal. Some things are. So like knapsack. Knapsack fractional is always optimal. Knapsack without fractional, knapsack 0,1, sometimes it's optimal, sometimes it's not. It depends on M, it depends on the sizes, it depends on the values. So that one varies. But Prim's is greedy and it's always optimal. Divide and conquer. So divide and conquer is when we have 2 or more subproblems that don't overlap. Dynamic programming is when we have overlapping subproblems, repeated subproblems, where we can memorize results and use them in the future instead of recalculating them. If we can sacrifice a reasonable amount of memory, we can make a significant savings in time. Now remember, divide and conquer, we also talked about combine and conquer. Combine and conquer is a subset of divide and conquer. So things like merge sort. Merge sort is divide and conquer, but more specifically, it's combine and conquer. Like I could say, you are a mammal. Well, that's true. I could be more specific though and say you're a human. So it's nice to say more specifically, merge sort is a combine and conquer, but it is a combine and conquer. Now, backtracking and branch and bound. Remember, backtracking is for constraint satisfaction, branch and bound is for optimization. If we don't have a function we're trying to optimize, we can't branch and bound. If we can't figure out a best so far, I mean, not a best so far, sorry, if we can't figure out an estimate of the remaining cost, we can still do backtracking. We can still prune things that are invalid, but we might not be able to prune things that are not looking good just because we cannot think of an estimator function. So to do branch and bound, you need an estimator function. You need a best so far. And as we saw in Project 4, having someone that can provide you a best so far that's better than infinity for a minimization or 0 for a maximization gives you a better starting point and lets you prune more. It's not required to do it, but it lets you prune more and faster. Now, dynamic programming, I'm going to get these into the video. Fibonacci, we've got here the terrifyingly bad recursive solution. Now, it says here write 2 versions of this function using top-down and bottom-up. So what family best describes this implementation? This implementation is brute force. It's not DP. It's not divide and conquer because it doesn't solve one half and then solve the other half. It has to solve both halves. So it's not divide and conquer because it's overlapping. It's not using DP. This is brute force. Now, I'm going to show you 2 different solutions to this for top down and bottom up. So that's the one that says brute force. So this is one that's a top down using a static unordered map. The advantage of this one is I don't need to know what's the biggest value that'll fit in an unsigned int 64T. I just say, hey, let the unordered map keep track of things, and if the value associated with an integer is wraps around to an invalid number, well, that's the user's fault. And here's a bottom-up solution that has O of 1 memory. It basically keeps track of 2 things. Well, 3 things. It keeps track of the previous, the current, and a temporary value, and uses some tricky math to basically move values between, like current becomes previous, etc. And so we're almost done here. So what have you learned this semester? Well, you've gone from the beginning of the semester of what do you mean we don't get starter files and we just have to code a few functions to Project 2, and oh my gosh, they gave us starter files and they were templated classes and deriving from templated classes, and we had to learn about this arrow compare because of, I just can't say this compare even though it's in the base class, to, now at the end of the semester, especially Project 3 was more complicated than Project 4 in terms of data, of designing your own data structures, laying out the data structures to make a solution, analyzing code, looking up things that you've never seen, like reading a paper about a pairing heap, reading websites about different TSP heuristics, making some design choices and implementing something you haven't seen before. So hopefully you have that feeling of how far you've come along the way. What do you do next? Upper level courses. So if you can get into an upper level course for fall, great. If you're already in one, they are not going to check prereqs yet. So we're good. Get that grade in for 281. It'll be done way before they check if people are in those classes without prereqs. So upper level classes, if you can't get an upper level, well then 370, 376, something like that. But if you can get an upper level, get into one. And then also start learning on your own. Start looking at other libraries and doing things like you've been doing of creating your own data structures to use. Okay, so that's it for today. We've got office hours today. We've got office hours. I know we have profs hours tomorrow and Wednesday. I don't think we have any Thursday because we need to make sure we finalize the exam and everything. But then exam will be like previously. Piazza will be set to private. You can post on Piazza if you've got questions. We'll get back to you as soon as possible. So we'll see you on Friday, and we hope you've had a good semester and learned a lot in 281. My end stream button is not working. Looks like I lost the internet right at the end here.